All right. Today I got a question on a really hard one here. So let me go ahead and try this one. This one is number 64, but it's from the university physics book, which is chapter 8, but it's equivalent of your chapter 7 of our main book here. And it simply says this. It says a block of mass 500 grams. Well, let me pause right there and point out that we probably need to be really careful with our units here, because as we start to do our energy is measured in units of joules, which has buried inside of it a kilogram. And so we got to go all the way back here to chapter 1 and be careful with our units. It is attached to a spring with a spring constant of 80 newtons per meter. So I'll put K 80, and the units are nice. They are in the base unit, so that's really nice. Let's see. The other end of the spring is attached to a support. The mass rests on a rough surface, so we've got to deal with friction. Coefficient of friction of 0.2. Okay, I'll keep that in the back of my mind. And it is inclined at an angle of 30 degrees. The block is pushed along the surface until the spring is compressed. There it is, 10 centimeters. Let me write that as 0.1 meters. Okay, so again, watch the units. And is released from rest. Okay, so initial speed is 0. A, how much potential energy is stored in the block spring support system when the block has just been released? Okay, so one of the important equations, and I'll just put A, that we did in our derivation of conservation of energy, we called it a potential energy due to a spring, or an elastic potential energy, not to be confused with gravitational potential energy, but it was a 1/2 kx squared. So in this case, I will put a 1/2, I will put an 80 newtons per meter, and the distance compressed or stretched is what that x means. And so this would be 0.1 meters and square it. And looking at the units, it looks like the meter downstairs would cancel with one of the two upstairs, and you'd be left with just a Newton times a meter, which is a joule. And so our unit analysis works right. We're asked for an energy and comes out in units of joules. So if I put in my numbers here and square it, I get 0.4. So 0.4 joules is the amount of what I would call initial elastic potential energy. All right. Now they start to get hard here. Here it says determine the speed of the block when it crosses the point when the spring is neither compressed or stretched, what I like to call its natural length. So if it was compressed down to here and it goes shooting back up, clearly the spring wants to push it up, but it has to overcome two other items, and that would be friction and gravity, in order to get it up the hill. Now, let's talk about it in terms of energy, not in terms of forces. We could go either direction with this, but it's a lot easier with energy because the force from the spring keeps varying. And so we wouldn't want to mess with that. So let's use the principle of conservation of energy. And like I said, we derived this and did all the integrals, so fortunately we just kind of have to remember how they were worked out and how they were derived, and that is actually challenging. So let's talk about those individually. But one of the energies we talked about was kinetic energy, so I would say initial kinetic energy. Another one is potential energies, plural, because in here we have the gravitational potential energy and we have the elastic potential energy. Then we have what we called work by non-conservative forces. And so other things involved that were friction and maybe something tied to it like a rope. Now for this problem we don't have that, but we do have friction. So this is really talking about the heat or the friction involved. So if we include all the energies we start with, that must equal all the energies we end with. And that phrase, initial and final, can be misleading. A better phrase might be to say the energy at one point is then equal to the energy at another point. So it doesn't have to be initial, it could be any point. And it doesn't have to be final, it can be any point. Because if I think about this, I might have a tough time really deciding what I mean by initial. Does initial mean right here where my hand pushes on it, or does initial mean when I release it? And then as it goes shooting up, what about final? Is final when it gets back to this point, or will this continue on because it's going at a large speed? And it sounds like it would, because that's the question. Determine the speed when it gets back here. And so then it would continue on up and maybe then come to a stop, which is what C is about. Determine the position of the block where it comes to rest. And of course, then if it comes to rest, then the spring would snap it back down. And so what do we mean by final position? And I'm going to say it's just any two positions. And what we mean by initial and final is just where we begin to think about it and where we end thinking about it. Not that it doesn't end its motion, and not that it didn't have existence before initial. So my definition of initial and final is going to be this. The initial is going to be here when it's compressed, and right after my hand lets go of it. So I know there was a bunch of stuff before that, but I'm just going to think of that as initial. So then it goes shooting up. And then I'm going to think of final as being when it gets back to the spot. I know that even after that, it keeps making some more motion, which is what we'll do when we go on to part C. So again, just for clarity, this initial and final really just means any 2 points, they are equal. And then I just need to be clear on what I'm going to call my initial and what I'm going to call my final. So hopefully I made it clear about those, because now I can go on and put in my equation here. So this would be a 1/2 mv initial squared. The two potential energies would be mgy initial, and the other would be 1/2 kx initial squared. The work, if you remember the derivation I did for the work, was a negative force of kinetic friction times distance traveled. So we're going to have to talk a lot about that. And then, of course, the final kinetic energy would be 1/2 mv final squared. And the final potential energies would be one from its gravitational height and one from the final position of the spring. Now, fortunately, depending on how we think about it and label it, we can have a number of these equaling to 0. Actually, we only have one option. We can pick the y equals to 0 anywhere we want. We can't call velocity equal to 0 anywhere we want, and we can't call x equals to 0 anywhere we want. In fact, it's probably worth pointing out that these x's and y's are not the two independent axes on a grid. This x was worked out for the distance that a spring is either stretched or compressed. So if I come back to the picture here, and maybe I put my grid right here, and so my traditional XY grid, and I put the origin right here at its lowest point or its beginning point, that can be helpful because that means this term right here is 0. In fact, I would recommend either picking the lowest point at 0 or the highest point at 0, or final point at 0, because then you have simpler equation. And since I prefer to use positive numbers than negative numbers, I will put the lowest point at 0, and then everything above that is positive numbers. Again, it could be done either way. But if you were to pick some other point other than the initial or final, then you would have numbers on both sides, and you'd have to introduce another variable for the distance of where you put in that origin. And then you would really make it hard. Not only are none of these zeros, but you got another variable to worry about. So it only makes sense to call either the initial or the final 0. And if you're like me and prefer to use the positive numbers over the negative numbers, my recommendation would call the lowest point 0. So that's what I'm going to do. I'm going to put the lowest point of 0, make that term 0, and it goes away. It's out of the equation. Now, I also want to emphasize we don't have that option for this 1/2 kx squared. Again, I know it seems like busy work during a lecture when the professor goes through all these derivations and these integrals, but the reason I did that is so you would know where these came from, and the fact that you won't have to do the integrals again. So we can solve this problem by just a bunch of algebra. We can just put in what we know. And if you remember the derivation of the x is how far the spring is either compressed or stretched. So sadly, we do not get to pick that to be anywhere we want. But also that means we need to be careful of where the x equals to 0, because I'll say it again, this x here is not this x. So when I talk about the spring being compressed to get it started, it's this distance, which I believe they told us right here is compressed 10 centimeters, 0.1 meters. So this term right here would be a 1/2 times an 80 times a 0.1 squared. And that's worth repeating here because, again, a beginning student could look at this and say, well, isn't the initial part right here, doesn't x equal 0 right there? And I'd say, on the x on the grid did. But the x in this equation is not the x on the grid. It's how much the spring is either compressed or stretched from its natural length. So that's why this x is not going to be 0, even though the origin I am placing is at this spot. So choosing the origin only helps me with the gravitational potential energy, doesn't really help me with the elastic energy. There, on the elastic potential energy, the x has to be 0 at the natural length of the spring. Which, by the way, is actually kind of helpful for this problem because that'll make that term 0. Because remember, for part B, it says that you want this to come back up to the point where the spring is neither compressed nor stretched. And so that means your x is 0 here. So even though I can't pick my x equals to 0, the way they asked the question was really nice. It gave me a chance to call that equal to 0. All right, so now let's see what else I have. They also said it started from rest. So the initial kinetic energy is 0. And, of course, we're looking for this v. What is its speed when it gets back there? Okay, so that one's not 0. Now, this y final probably can be seen in this picture. If it went up the incline, as we're saying, 0.1, it would have gained a height of 0.1 and then opposite of 30 degrees. So its height would be 0.1 times sine 30. And sine 30 is a half. So this would be 0.05 for how high it goes. So I can take advantage of the angle and the distance of the spring in order to figure out how high it goes. And that's what I'm going to need right here. Okay. Now, maybe we should mention a little bit about this one. Going back a couple of chapters, the force of friction is the coefficient times the normal. And the normal, when we're on a hill like this, is mg cosine theta. Now, we did this one a lot, so maybe I'll just kind of draw the picture real quick. But if I had a block on a hill, I would say gravity is pulling it down. There's mg, and normal force is off at an angle. And that's really enough to solve the problem, but I guess technically for this one, we'd have a force from the spring pushing it up, and we would have the force of friction pushing down as the thing is sliding up. But as far as perpendicular to the incline, I can look at this mg and say that this component into the hill, into the incline, is adjacent to the mg. So it would be mg cosine theta. And so the only force pushing it off the hill is n, and this force of gravity is the only one where a component is in here. And those have to balance each other. That is, n minus the component from gravity has to be 0. So this mg cosine theta is the normal force. And that's what I remembered from a couple chapters ago. So I'm just going to put that for my force of friction. All right, well, we've done a lot here, and we got a lot more to do. Let me go ahead and kind of summarize and clean up all this that we've done so far. So the first two terms are 0, and then we get this 1/2 80 times 0.1 squared, which is part A calculation. So this is 0.4 joules there. Now, this one here, as we just talked about then, would be a minus. And as I put in the coefficient of friction, which is 0.2, and then this mg cosine theta, let's see, what's m here? 0.5 for the m. G is the 9.8. Cosine 30. And then, of course, the distance it traveled, well, that's just along the incline, so that is the 0.1. Notice it's not the vertical distance, it's actually the distance traveled, so it's along the incline. So this distance would be the 0.1. Let me just make sure I got everything. Coefficient, mg, cosine 30, distance traveled. Okay, good. So that's that term. Then that has to equal, and why don't I just leave this for a moment as 1/2 mv final squared, because this one here we talked about would be mg, and then the height we worked out. So the m is the 0.5, the g is the 9.8, and the height traveled is the 0.05. Okay. And so now I can figure out these other two numbers. So this number here would be 0.2 times 0.5 times 9.8 times cosine of 30 degrees. Oh, yeah, and then times 0.1. There's what I'm missing. I was like, whoa, that's a weird number. Okay, so this is 0.0849. So that's the first little bit of energy taken away from the compressed spring. And the compressed spring has to give that energy to its height. So 0.5 times 9.8 times 0.05 would be a 0.245. So if I take this 0.4 and subtract this number. And then also subtract this number. I get 0.0701. And then, if I multiply it by 2 and divide by the mass, which is 0.5, I would get the velocity squared. And then taking the square root would be 0.529. Okay. So there would be the velocity when it gets back to its main point, or its natural length is what I should say. Its equilibrium point. That's what I'm looking for. Now, it's, again, a long problem, because we now have part C. It says determine the position of the block where it comes to rest. So I'm going to do the same logic, initial and final. And I kind of have a choice to make here. Remember, this initial and final is really any one point compared to another point. So when this thing goes past equilibrium and goes up to here, it slows down and eventually comes to a stop because it's got to fight gravity, it's got to fight friction, and it's got to fight the stretching of this spring. So remember, as it goes up, the spring is still attached. That's important here. And so there's 3 reasons why this thing will slow down. And so it doesn't have much of a speed, but it does have some speed, and so it's going to continue on up for a little bit. And there's 3 factors keeping it from going very far. So I will call my final position up here. Well, now my initial could be all the way back here where I started, or I could then say maybe my initial for C is my final for part 2. It doesn't really matter because as we did part B, remember, this side for part B was the initial way back where the spring was compressed, and this is when it gets back to equilibrium. And so this final is equal to the initial. And so I could now call this final the initial of the second one if I want. It doesn't really matter. They're the same energy. I could call any point during this motion the initial because they all have the same energy. And there's a couple advantages of either way, but I think there might be more of an advantage if I call the ending point of B the beginning point of C. So let me do that. And then again, I'll say initial kinetic plus initial potential energies plus work done by the non-conservative forces equals the final kinetic energy and the final potential energies. And so over here, then, if I am referring to this as the initial as it goes on up, I would then be saying, why don't I then rethink about where my grid is and put my grid there? That's the lowest point. And that way, when I do the MGY initial, I can say that's 0. And also the other potential energy, the 1/2 kx initial squared, would also be a 0. And that's kind of what was going through my mind when I go, okay, well, maybe I should think about this as the new initial, because if I take this as the new initial and set y equal to 0 there, both potential energies, the potential energy from gravity and the potential energy from the spring, would be 0. And so I kind of like that. And so that's why when I was kind of debating which one to call, I said, let's call this the initial. So the ending of B becomes the beginning of C. And that's, like I said, kind of what I was thinking here. Now, of course, it's moving. So this would have a 1/2 times mv initial squared. And I'll put those numbers in a second. But I would also then have this non-conservative force, mu mg cosine of 30 times d for the work done. But let me be careful with this d. What we'd be talking about in this part C is that d is this distance up here. How far does it, move along from my starting to my ending? And that is a number I don't know. Of course, that's what we're asking for right here, right? Determine the position. So there becomes what we're hunting for in this problem, this d. And so hopefully the other things I do know. And I think I do. I'll put them in. I have a 1/2. I have a mass of 0.5. I have a speed that I got earlier is 0.529 squared. And then I can go minus the coefficient, which is the 0.2. The mass is 0.5. The g is 9.8. The cosine of 30 is the root 3 over 2. And then there's the unknown d. And so if I put in the numbers I know here on the left-hand side, I'd have a 1/2 times a 0.5 times a 0.529 squared, and that would be a 0.0700 minus, and this would be a 0.2 times a 0.5 times a 9.8 times a cosine of 30, and this would be 0.849d. Now, the other side of the equation right here, this would be 1/2 mv final squared. That one would be 0. That's what was told here in part C. Determine the position where the block just comes to rest. So it goes up the hill and has a speed of 0. But you see, now I would have both potential energies. I would have an mgy final, and I would have a stretching of the spring. Now, let's talk about both of these and come back to the picture, because for final height, I can do a lot like I did in B and see what the vertical height is. The vertical height would be the hypotenuse, which we don't know, it's d, but it would be d times the sine of 30. So that means I could write this term here as mg d sine 30 degrees. And then this term, the x, is how far did it stretch. And coming back to the picture, as it goes up the hill, it stretches the spring by a distance of d. So this would be a 1/2 k d squared. So again, if we put in the numbers we know, let's look at this first term. The mass is 0.5. G is 9.8. D I don't know. Times, and sine of 30 is 1/2. I'm going to get a 2.45 d here. And then this 1/2 k, remember, is 80. So that would be 40 d squared. So I do have all the information except for d. And I suppose maybe a bummer part is it's a quadratic equation. So I've got some algebra to do to solve for d. And it looks like this 245, and bring this over. So if I add it to 0.849, I'm looking at a plus 3.30 d, and then minus a 0.07 for c. I'm sorry, for the constant. And then I'm thinking in my mind of solving a quadratic equation and figuring out what the variable is, which is d. Says it's the opposite of b, so negative 3.3, plus or minus b squared, so 3.3 squared, minus 4 times the a, that's a 40, times a c, which is a negative, and I'm just going to put that negative right there, so that becomes a plus, and then 0.07, all over 2a. And now I'll get a number. Okay, now, I would notice that there's a plus or a minus. Let's talk about that, but just to have something to work with here, let's do this little square root. So 3.3 squared plus 4 times 40 times 0.07, and then the square root of all that. Okay. Now notice then, if I take the negative together with that negative, this would all be negative, and I'd get a negative distance for d. It's not the one I want. The one I want is going to be the positive then, the one that goes up the hill. That negative one would be saying, what if it had that speed being pushed down? How far would it go before it came to a stop? So there's a meaning for this negative one, but it's not the one I want. So if you'll allow me, then I'll take the positive one and combine it then with the negative 3.3. And then divide that by 80 downstairs, and I get 0.0175 meters. And I'm a little wishing I had carried more decimal places at this point, because this is such a small number that this whole difference between here and here is significant. So I'm not sure how far to go with the significant figures, but oh, I know. I'll look up the answers here, and hopefully it's something close to that. Let's see what we got. Yeah. See, let's just check. So in A, oh, good. So we got the same number in A. That's good. And then B, we got nearly the same number. In B, the author says 0.53. Okay. Now in C, though, we are a little bit off. Your author is saying here 16. Oh, wait. 0.06. I paused for a second because your author put 16 centimeters. And that meant my answer was way off. But I decided after looking at this that I think this is where your author made a mistake. I think your author meant to put 0.016, or maybe your author meant to put 16 millimeters. But with 16 centimeters, that's actually more than the original compressing of the spring. And so if there was no friction and no uphill, when you compress at 0.1, it would go back and extend to 0.1 and then come back. It would never go to 0.16. And given that it's going uphill and with friction, it'll be a lot less than this. And so I think there was just a typo on your author's point. I think he really meant to put 16 millimeters for the solution. And that would be somewhat close to mine. And like I said, with reasonable decimal places, that makes sense. All right. So I feel good about it, even though it surprised me there for a moment when I had a different answer than your author. But I think in this case, the author made a mistake. Okay. Hope that helps. Take care.